Today I'm taking apart and figuring out the portable power station from Aferiy Nomad 1800, or the short name for the station is P180. Aferiy stopped selling the 1200 watt stations, and now they've been replaced by the 1800 watt station. The price is €449, and that's the price without a promo code. You'll find a promo code in the video description. Shipping across all of Europe is totally free. Inside, there's a lithium iron phosphate battery with a capacity of 1024 watt hours. The same capacity was in the 1200 watt station. The station's dimensions have remained the same, and the station weighs 11.6 kilograms, but now the station has a more powerful inverter. The rated power is 1800 watts and the peak power is 3600 volt amperes. The package includes a cable for charging from portable solar panels and from the AC power grid. There is no car cable included. The station's cooling system is designed so that the station operates quietly, even under a load of 1600 W. It runs very quietly, and the noise near the station will be 45 decibels. Even at night, this is a comfortable noise level. On the front panel, there is a power button. It also features a dedicated flashlight button for illumination, along with a separate power button used to activate the various USB charging ports and DC output sockets for your devices. This station has two USB-A ports with 18 watt power, a Type-C with power delivery 20 watts, and one Type-C port with power delivery 3.1 at 140 watts. And besides power delivery 3.1 at 140 watts, it also supports the digital UFCS protocol at 50 watt. On the other Type-C port, there is power delivery 3.0 at 20 watt, quick charge 3.0, and also fast charging protocols for Huawei and Samsung. As for the DC ports, everything's pretty standard. 12 versus DC ports, 5.5 by 2.1, and one, a car socket at 12 volts, 10 amps. And just like on other stations, on this socket the voltage is 13.9 volts. It's kind of an imitation of a passenger car's onboard network. I have the European version, so on the back panel there are two outlets for 230 volts, 50 hertz, a black overload protection button, and a button to turn on the 230 volt output. And on this station, none of the buttons are backlit. They didn't really bother with charging power. There are two options. Either charge at 500 watts, the battery, or at 1000 watts, but in the settings there's a quiet charging mode which allows you to charge the station at 400 watts. This is the AC input, and next to it, it says 1000 watts maximum, and that's the maximum power indicated for charging the batteries from the AC mains. In bypass mode, the station can pass through up to 1800 watts. The XT60 connector is for charging the station from a solar panel or an external battery. The voltage range is from 11.5 volts to 55 volts. The maximum current is 15 amps, and the maximum power is 500 watts. And there is a warning that you must not supply more voltage, 55V, to this connector. So the optimal option for charging this station would be 24-volt batteries. And from 24-volt battery, this station charges at almost 400 watts of power. The station's compact, lightweight, and it's quite convenient to carry with one hand. And now it's time to put a load on the station and see how it'll actually handle the load. An oil heater at maximum power consumes 1600 watts. The noise is relatively low. Around the station itself, it's about 50 dB. Now I'll try to overload it with a hairdryer at 2.2 kilowatts. And at maximum heat, the hairdryer was drawn about 1800 watts from the station. That surprised me. It turned out that under such a load, the output volt of the station drops from 233 volts to 225 volts. And the smart socket showed that the hairdryer was consuming 1826 watts. But if you run this hairdryer, the city grid, the smart socket shows almost 1900 watts, so the station is able to handle the load by lowering the output voltage of the station itself. A 2 kilowatt electric kettle, when plugged into the city grid at 230 volts, draws 1923 watts. And even from this small station, the 2 kilowatt kettle was able to work. The station reduced the output voltage 223V, and the output power of the station was 1814 watts. But this function will only work with resistive loads, such as heating devices. For example, an electric kettle, a regular electric stove with a power of 1 kilowatt. The stove is cheap and overheats quickly. And with stations like these, it's better to use stoves with 1.5 or 2 kilowatts. And so to boil 1 liter of water using this stove, almost 20% of the energy charge was used. To make 300 milliliters of coffee using a 500 watt. When using this electric kettle, it only consumed about 4% of the total energy. The station's peak power allows you to even run non-inverters, refrigerators, but my refrigerator is an inverter model, and the station's energy reserve was enough for 21 hours of operation for this refrigerator, and during that time, 580 watt hours. All the remaining energy was consumed by the station itself. But on that day, we didn't use the refrigerator much, and the apartment was cool, about 20 degrees Celsius. A full discharge using an oil heater is the fastest way to drain it, and the station delivered 912 watt hours. A 100 watt discharge through the Type-C port, and the station delivered 915 watt hours. The station has 3 charging modes, 1000 watts, 500 watts, and a quad charging mode. At a charging power of 1000 watts, the station charges up to 80%, 45 minutes. Then it halves the charging power and fully charges to 100% in an hour and 40 minutes. If you choose a charging power of 500, the station will charge from 0 to 100% in 2 hours and 20 minutes. And with quiet charging, it'll charge at 400 watts and it will fully charge in 2 hours and 30 minutes. The recommendation for charging the station is the same as for other stations. If possible, do not charge it at high power. The station outputs a perfect sine wave, but if you load it with a 2.2 kilowatt hairdryer, you'll notice both a decrease in amplitude and distortion of the sine wave. This station can also work as an uninterruptible power supply. The technical documentation states that the switching time is 10 milliseconds. I took several snapshots, and indeed, the switching time is about 10 milliseconds. My computer doesn't even notice these switchovers. This station is made by the Chinese company SYD, so the app used is Bright EMS, and this app works very slowly. The app has output control, a discharge and charge graph, a charging graph from solar inputs. The station settings, you can turn off key sounds, and there's also the option to remotely turn off the station. Other languages are available. There's energy management. You can set the lower limit for discharge and the upper limit for charging. And here I recommend specifying only the lower discharge limit at 5%. When the discharge reaches 10%, the station will emit an audible signal. And that sound will be enough for you to know that the station's charge will run out soon. In the charging settings, you can enable quiet charging, and then the station will charge at a power of 400 W. There is scheduled charging. Changing the DC input type, unfortunately, does not work. It will always be in PV mode. That's the mode for charging from solar panels. And in this mode, there is a limitation. If the input voltage is up to 14 volts, the station will draw no more than 100 watts. The current that the station will draw through the solar panel can be limited from 1 to 15A. The time after which the screen will turn off. The station can also turn off automatically. If it is running on batteries, then there is no load. For both AC and DC outputs, it can either never turn off or turn off after 8, 16, or 24 hours. The app showed that there is a firmware update available for the BMS, but I couldn't update it because a password is required for the update. I've already written to the sellers, so now I'm waiting for them to send me the password for the update. And when I first turned it on, I saw errors in the fault log. They indicate the voltage coming into the solar panel input is too high, but to the solar, nothing had been connected to the input at that moment yet. Starting from version 1.6.0 in the Bright EMS app, some things have changed regarding integration with the Home Assistant Smart Home. For example, in the profile section of the settings, a local MQTT broker setting appeared. This is the configuration for the local message broker server. The FosseBot integration has also been updated, but unfortunately at the time of filming this video, it's still not possible to use the station with this integration because the station is transmitting unclear data. Maybe it will work after an update, but I'll check after the station is updated. Now let's take it apart and see what's inside. To take it apart, you need to unscrew the long studs and then remove the top plastic cover, which is held by clips. And you need to do this carefully because the clips can break. The side panels come off easily, especially if you unscrew the screw hidden deep inside. And this is what the inverter and charger board looks like. The internal battery pack consists of 16 individual lithium-ion battery cells. On each side of the unit, there are two quiet cooling fans strategically positioned to maintain optimal temperatures. The fans are controlled by voltage. The inverter board is screwed onto the plastic part of the case, and underneath it are the BMS board and the batteries. It seemed to me that the heat sinks here aren't very big for this level of power, but the four fans do their job. The transformers use Litz wire, and the label SYD refers to the company that makes these stations, Sunyanda. N113 is the model number, the name of this model. Capacitors and heat sinks for the high voltage section. When I removed the top cover, I damaged one of the clips. Right at the main input section, there is a protective choke, several common mode chokes, filtering capacitors, and protective varistors. You will also find two 12-amp relays, while this specific relay is rated for 8 amps. The electrical power coming from the BMS flows directly to the board right here. The inverter receives power through two screws. The battery pack was made on January 14th, 2026. It uses 16 LFP cells with a capacity of 20 amp hours. The manufacturer is Eve. The production date is November 24th, 2025. From the battery, a metal bus bar runs from the batteries to the BMS board. Pay attention to the heatsink of the low voltage section. It is screwed to the board through a thermal pad, and the transistors are located on the other side. 4 high voltage transistors of the section are on thermal based, and these are 60 amp 650 volt transistors, and these are IGBT transistors. On the smaller sized heatsink, there are para power transistors, and these are also high voltage transistors which are specifically rated for a maximum of 650 volts. 53A. On the backside of the inverter board, there are drivers and transistors. Of the low voltage section, the current carrying traces are reinforced, and as transistors, toll package transistors are used, but I couldn't find detailed information about these transistors. Usually MOSFETs in TOL packages can handle quite a large current. As for the drivers, the SL2110 is used, and this is the BMS board. The current carrying traces are reinforced, and toll package transistors are used as charging, discharging switches. There are some unpopulated connectors on this BMS. This same BMS will also be used in the next model, the Nomad 1800 Pro, and the Nomad 1800 Pro will have an expansion port for battery packs, and the same BMS will also be used in the backpacks. Next to the battery contacts, there are 4 50-amp fuses, and this is probably the biggest pain point for all power stations. This is a passive balancer with 47 ohm resistors. So the balancing current is 75 milliamps, and there's 16 resistors here. The battery configuration is 16S. The nominal battery voltage is 51.2 volts, and the transistors on this BMS are rated for currents up to 290 amps and for voltages up to 100 volts. On the BMS board, there are found suppressor diodes, 4 pre-charged system resistors, and contacts for connecting to the inverter board. The panel has a microcontroller and a Wi-Fi adapter, and I was surprised that an STM microcontroller is used here because usually on Chinese, portable charging stations use Chinese microcontrollers, and the Wi-Fi Bluetooth adapter is based on the ESP3-C3. Near the cigarette lighter output, I found a very strange curved metal part. The device features a high-resolution screen, an integrated buzzer, and a powerful 3-watt LED flashlight for illumination. The specific Type-C controller utilized in this design is the SW2335 model. Furthermore, this advanced chip provides full support for the UFCS 50-watt fast charging protocol, ensuring high efficiency. And now we can draw a conclusion. This small station delivers the state power of 1800 watts, but the station's inverter can also lower the voltage when more powerful active consumers are connected. The main advantage of this station is that it operates very quietly, but the use of transistors and TLL packages will make repairing this station a bit more difficult. But now, almost all manufacturers of charging stations are switching to this type of component base. Another drawback is the passive balancer, but again, most charging stations, a passive balancer is used. So if you use the station in UPS mode, don't forget to occasionally disconnect it from the grid and let the station discharge and recharge. And unfortunately, using the proprietary app from SID Bright EMS significantly limits the functions of this station. Compared to the Fossabot 1800, this station is quieter, but Fossabot has completely switched to their own software and they've added new features. That's where I'll wrap up the video. Just a reminder that the previous station with 1200 watt capacity cost about the same. That's €449. And that's all for now.